So it's time, let's get back to business. So last time we did something rather profound. We did the first order perturbation calculation for a helium ground state. And then we also treats it into a variational calculation. The results become better and better in comparison with the actual value. And more than that, in these two calculations, there is one integral that came out. And first of all, we were discussing that this integral has a classical electromagnetic theory interpretation. And today we will continue on and we will turn it into I think the most powerful quantum mechanical calculation of all time. Namely, if we understand the meaning of this integral, it will help us establish a powerful calculation method that can work for all the atoms, all the molecules, and all the solids. In fact, that plays an important role in our understanding of atoms, molecules, and solids. So let's move on. So this is the plan for today. So this is the integral that we played with. The TA calculated it exactly this week. I think the solution has been posted. And it has a classical electromagnetism interpretation. Namely, it looks as if the two electrons, according to the unknown wave function or known wave function in the perturbation calculation, there's a bit of charge here, a bit of charge there. They interact through the Coulomb repulsion potential energy. So that could be generalized to the case where the two electrons are now in different wave function, different single particle wave function A and B. As long as it is of this form, it allows a classical physics Coulomb interpretation. In the discussion, I hinted at something non-classical, entirely quantum. It is called the exchange integral. I give the integral in equation 28. At this point, you only need to stare at it long enough so that you convince yourself there is no classical physics interpretation. We haven't talked about when this integral will appear, but hold on to that. You will see that it will appear soon, especially when we consider the excited state of a helium atom. So we stopped it on the previous page last time. So let's start from this particular page. Equation 26 here is exactly the Coulomb integral that we discussed. And that can be calculated exactly if this is taken to be a hydrogen-like wave function. Now, I will write it in a slightly different form. I single out the R1 coordinates, one on the left, 1s, one on the right, and then the integral over the first electron's coordinates. Then I realized that it is of the form of an expectation value, right? If I focus on the electron number 1, so-called, with coordinates R1, it looks exactly like the expectation value, two wave functions, one on the other side, one on each side, and then we have some operator in between. And we also know how to interpret this operator. This is just the potential energy that electron number 1, this one thing, cease due to electron 2, which is in some state called phi 1s. So it is this bit of charge E times psi 1s R2 due to electron number 2, and then it will create a potential energy at R1. So this bracket in between is a function of R1. Therefore, it hints at that we can regard as electron number 2 now producing an effective potential acting on the electron number 1 that we are focusing on. So this is a very suggesting form, so that we now can reduce a 2-electron problem into some effective single electron problem. So the idea that emerges from this interpretation is as follows. Let me repeat it one more time. Now, the bracket in the middle is suggesting us to regard the effect of electron number 2 as producing an effective potential energy function that is acting on electron number 1. So now we can think about electron number 1 alone. It has its kinetic energy term. It sees the nucleus attraction, no doubt. Now, what is happening to electron number 1 due to the electron-electron repulsion of electron number 2? This expression tells us that we can regard it just as an extra potential energy term acting on electron number 1. Okay, so now suddenly that is the big step in the development of many electron atomic physics. So all of a sudden, we can now regard electron number 2 as producing an effective potential on electron number 1. All right. So let's get back to the picture of we are doing variational calculation. So we can make a guess that the ground state helium wave function is someone as yet to be determined state. So this phi 1s is an unknown. Okay, but we know the ground state is something like we have one electron in the 1s state, another electron also in the 1s state. However, now the 1s state is to be determined. Now with this, we can set up, when we do the calculation for variational calculation, we will meet this integral. We did that last time. And then with the same interpretation, we know that electron number 1 is seeing an effective potential energy repulsive form from electron number 2. So thereby, suddenly, we have a single electron Schrödinger equation to solve for the unknown 1s wave function. This box, if you understand it, it will be a step forward in your maturity in physics and in your knowledge in quantum mechanics. So pay attention to this. So in my calculation of the 1s helium state, I guess an unknown wave function. I put 2 electrons both in this state, but I don't know this state. Therefore, I need to solve for this state. After writing out the energy I need to calculate, then I realize at least approximately electron number 2 is producing this kind of electromagnetic potential energy term acting on electron number 1. So I can simply use physics without derivation. This can be derived rather formally, but you need some higher level mathematics. But using physics is sufficient for our purpose. So if I focus on electron number 1, then electron number 1 sees the attractive +2e nuclear charge. So this is the highlighted term. Electron number 1 has its own kinetic energy term. So that is the first term. Now, it comes to the key point. I want to reduce the problem to solving single electron states. And now I have this 1s state to solve. But in solving it, I must recognize this is a 2-electron problem in essence. We cannot completely ignore the second electron. So now we want to take into account, at least in an approximated way, the effect of electron number 2 on electron number 1. After seeing all these Coulomb integrals, we know what to do. Electron number 2 is providing such a potential energy on electron number 1. Notice that this is an integral over electron number 2's coordinate. This has a R1 here, thereby after integrating R2 out, this is a function of R1. So basically, this is an effective Coulomb electron-electron repulsive potential energy depending on the coordinate R1. So look at this. Finally, we have one equation to solve for our unknown 1s state, as well as an unknown energy that I call epsilon 1s. This can be regarded as the energy for the helium 1s state, okay, later. So now I hope to pause here, because if you get through this box, equation 31, then the rest is easy. You understand? So there's a question, let me see. Is the reason why we can only approximate every time due to the fact that we need first electron to affect potential for 2, but at the same time, the same thing for the second electron? Yes, in fact, if we want to focus on electron number 2, we can write down a similar equation, but now in the potential energy term, we integrate over the first electron, then providing a potential on the second electron. The equation turns out to be identical in this ground state helium atom case. Okay, good question. Let me see. There's another question to me. So we assume all electron follows behavior separately, interacting only via the effective potential. That was the question. Mr. Chen, yes, at this point, we are making such an approximation, okay? Whether it's good or bad, at the end, physics is an experimental science. So you need to compare with some best result. Another question flies in. So is it a variational method? Yes. In principle, behind this method, it is variational principle that is working. So any further questions? Do you understand this box? This is a big business. You go to the chemistry department, ask around, see whether your classmates understand it. Because this is the beginning of the whole subject of quantum chemistry. There is a question about screening effect from Mr. Lee. Hold on to that. We are including some screening effect through this term. Okay, now this is completely attractive. The nucleus, now this is positive, therefore it will screen out something. So we are accounting for some screening effect. Okay, so another question comes in, why it is called a mean field theory. Okay, because I'm averaging out all the positions of electron number 2 in providing an effective field or effective potential energy acting on number 1. So in essence, this is a mean field theory. So it can be actually non-even. I don't understand this particular question. What is non-even? You mean I'm not treating electron 1 and electron 2 on the same footing? There's a question about I'm doing something non-even.
Yes, I mean that.
Okay.
So for now, we treat electron
1
as
we focus on
whole
1,
screen.
Right, and then see what electron 2 is doing to number 1. You understand that?
Okay.
At least up to here. Now,
okay.
I encourage you to think the other way around. You write down another equation, focusing on electron number 2. Okay, so you have this thing being R2. Do you understand me? This thing being R2, this thing being R2. Okay, and now you integrate this thing being R1 now. You want to focus on what R1 is doing to R2. Okay, you write down another equation. Do you understand me? Tai? Is that you?
Yes, yes.
Okay, now you write it down. So you have 2 equations. Okay, in principle, that forms a set of equations to be solved for, 2,1s R1, 5,1s R2, but they are the same function. So immediately you will see the equations are identical. Okay. All right, so now let me move on, and then at the end you may already understand what you want to ask further. Okay, so this is a big step forward. Suddenly we realize there is a way to reduce a 2-electron problem into single electron problems. Actually, it is problems. As the other student Tai just asked, I could have written down a second equation, also a single electron state equation, so that there are 2 single particle Schrödinger-like equations. Okay, now I put a Schrödinger-like here because indeed it is like a single electron operator, H, some kind of effective, psi equals some unknown energy and the energy eigenstate. But it's just like for the following reason. So I copied the equation here just for a convenience. In standard textbook notations, well, we are using R1, R2 for the 2 electrons. More ordinarily, the authors will use R for R1, the one that we are focusing on, and then R prime for the one that we are looking for the effective effect, the effective potential. Okay, so it's the same thing, only replacing R prime, R1, R2 by R prime. But at this point, there is a big idea here. In order to solve this equation, there is one troublesome situation. We want to solve the unknown phi1s. This is the trial wave function. I skip all the superscript for simplicity. We want to solve this. But in order to solve this, this is the unknown. The unknown is needed to create the effective potential. Okay, this is a point that you should realize. So do you understand that? There's something we want to solve. But in order to solve this equation, we need to know that something. Follow? Follow? 得唔得？得唔得？明唔明啊？ Okay, so that comes to your technique in computational physics. All right, so here is a breakthrough in the development of physics and chemistry combined. So in order to solve this thing, the technique is called self-consistent solutions. In 中文 is 技巧. What does it mean? Well, you can make an initial guess. Then you can go on to calculate this thing. I mean, calculate this thing out. All right. So basically, it's calculating a charge density using your guess. And then this is the Coulomb potential due to this guessed charge density. Then this is known. You construct this Schrödinger-like equation, you solve for the phi1s again. So you have an input for this, you have an output for the same function. You compare the input to the output. If they are very different, then your guess is very wrong. You tune your initial guess to a new guess, plug it in here again as new input, then you get a new output, compare again, no good, do it again and again until you set a tolerance. Okay, if the input and the output agree within your tolerance level, then you said, you got a self-consistent solution. So do you understand this iterative calculation to get to self-consistency? This is a key concept. Do you understand? I don't require you to do calculations here because you will have opportunities if you do projects, if you do some other things. But at least you need to know the concept. Okay, so in doing this calculation iteratively, at the end, when you have the input equals inputs equal outputs, of course, automatically you also get an epsilon 1s. Okay, so after many loops, you can solve for this phi1s and epsilon 1s. Okay, now let me tell you the name. I don't like names, so much names in physics. Now, if you understand this setup, then you should know the name of this equation or this method. This is the famous Hartree approximation, or also called self-consistent field theory. Hartree approximation applied it to the helium ground state problem. Well, it implies many things, right? We can apply Hartree approximation to lithium, to many other atoms. That's true. I'm just introducing it in the simplest situation, the helium ground state. Okay, so let's say you have done this loop to consistency. Then we know what is our optimal ground state wave function. We are guessing this. So after you get this, you know what this is. Now, you have to use this again to calculate the helium ground state energy. Very easy. We are doing variational calculations, so you get the optimum thing. You do the expectation value calculation with the full Hamiltonian of helium atom in the middle and your best guess on both sides. This is your Hartree level estimate of the helium ground state energy. Now, naively, some of you may think, I get this 1s state, and then my picture is I put 2 electrons into 2 1s state. The energy should be epsilon 1s plus epsilon 1s. Sorry, that is conceptually wrong. If you follow what we are doing, we are just finding the single electron best guess wave function. Okay, and then we have to go back to the 2-body problem and do the expectation value in order to get the ground state estimate, the ground state energy estimate. Okay, so this is the idea behind Hartree approximation, a very powerful thing. Now, I told you that we are not going to ask you to do any calculations of this kind, because of one simple fact. If you understand the principle, you don't need to write your programs. There are commercial packages that you can buy. I think many chemistry labs have a copy. For example, look for Gaussian.com. That is the best, I would not say the best, but most popular product on the market. They keep on updating their software. They call it Gaussian. I think the latest version is Gaussian 2016. So it is called Gaussian 16. Go to their website, look at the introduction to their product, how many methods they have. I think Hartree fork is rather high on the list. I looked at it yesterday. For those who want to write your own program, don't worry. Look up this book by Kunin, a Caltech professor, Computational Physics. There is a chapter particularly on this self-consistent helium atom ground state problem. And in an appendix, there is a program given to you. So if you don't like, well, if you want to write your own program, but you don't like to write your own program, this is the place to look at. So now I would like to claim the results. After you do all this calculation, epsilon 1s is found to be minus 0.8605 Hartree. So it's about minus 23 eV. This is actually in good comparison with what is called the ionization energy. That is to say, I have a helium atom in ground state, how much energy I need to take one electron from a neutral atom, take that electron out and free it from the atom. That is the ionization energy. So the epsilon 1s has some physical meaning. It is related to the first ionization energy, but it is not directly related to the ground state energy of the whole atom. We need to do another expectation value. Then, if we do all this thing, the ground state energy of the helium atom is this number. Okay, last time we have compared the first order perturbation variational calculation is getting closer and closer. This one is actually even closer to the actual value. So some question remains, what if I want to get the excited state? So in excited state, our mind is, we have one electron in 1s, another electron in helium 2s. Then I have two different states in my wave function. I think it's easy to imagine. You will have two equations now. I focus on one electron in 1s, then the other electrons is in 2s, producing the potential energy term. If I'm focusing on the electron in the 2s, the Schrödinger-like equation will have another electron in 1s producing the term, the effective potential energy term. Okay? And now Mr. Lee is rather clear that for electron number 2, which is farther away, the term provided by electron number 1 is now screening off some nuclear charge. Do you see? So it's already there. Okay? So you have two equations coupled, and then you need to do self-consistent calculation by making two guesses, phi 1s, phi 2s. At the beginning, you get two things output, you compare the pair, you do the loop, but only now you need to solve a coupled set of self-consistent equations. That can be done for excited states. But in our course, I just want to convey the main concept. Later on, if you really need that in solid state physics calculation, in molecules calculation, using a package, at least you know what the program is doing. Okay? So, can I still use different phi for ground state? Well, I think no, because in ground state, we have some single electron state picture, right? Relying on our hydrogen knowledge. The question is still, can I still use different phi in ground state, for ground state? My answer is, we have some single electron state picture for the helium ground state. Our picture is one electron in 1s, another electron in 1s. We haven't talked about how to arrange the spin yet. That is the Pauli exclusion principle. I just upload the notes for that part 30 minutes ago. Okay? Yes, because it's one atom. There shouldn't be two different 1s state. Okay? But if we move on to do excited state, then we will have one 1s wave function to solve and a different 2s wave function to solve. Do you understand, Mr. Chan? Okay. So this is the last page of the story. All right. Now, it is slightly abstract, looks complicated, but in reality, you don't need to do any calculation. Okay. But the concept is very meaningful in your advancement in physics knowledge. Okay. So this page pulls us back. Let me summarize. at least within this scheme, rather high-level scheme, we now realize a problem in an atom with Z electrons can indeed be regarded as single electron problems under the situation that we consider the remaining Z-1 electrons as providing an effective repulsive Coulomb potential energy acting on the single electron that we are focusing on. Okay? With this, it started to emerge as a single electron problem. That is the basis of what is called the independent approximation in atomic physics. This simply means we reduce everything to single electron state calculations. So that ends this part. The next section will continue on with single electron approximation. So let me look that up. So that hook up naturally to the next section, which is much simpler. Okay, so this section formally introduced the name independent particle approximation. All in all, that is the goal. We want to reduce Z electron atoms problem to single electron problems. Okay. Here, I marked it as a baby level discussion because the higher level discussion has to do with what we just did, the self-consistent iterative calculations. So after we have this hard tree idea, we know that we can focusing on one electron and then write down this effective single electron equations and then start doing the calculation and look for the energy for atomic states. For example, in bigger atoms, we may need to solve a couple of set of many equations to look for 1s, 2s, 2p, 3s, 3p, 3d, etc. These solutions in chemistry language, they are called atomic orbitals, or just atomic wave functions, if you like. So what we have discussed is the following, actually. Now generalized it to bigger atoms, but without the calculations, all right? So if I have atomic number Z, the nucleus will be plus ZE charge, positive. I have Z electrons. After we do a lot of things, hard tree things, self-consistent thing, we can reduce it to focusing on one electron, and the other Z-1 electrons now provide a effective single electron potential energy function. That is to say, in this thing, actually, the Z-1 coordinates are integrated over and live with only one coordinate. That is where our focusing electron sits. All right. So in a schematic way, within our previous discussion, we know the form of the equation. It must look something like this. The one that I single out to look for the solution, it has a kinetic energy term. It sees the whole nucleus, and all the Z-1 electrons will provide a repulsive, effective, single electron potential energy function. And that will construct a Schrödinger-like equation for us to solve. Now, if I combine this positive, this attractive, a negative attractive term from the nucleus and this repulsive term from the other electrons, it looks really like a single electron problem. These two can combine into an effective potential on the electron, and then this equation really like a Schrödinger equation. But as students in this particular course at CUHK, I really want you to understand there is a lot of hard work behind such a simple looking equation as we just discussed. This looping, self-consistent calculation. So remarks, this looks like a single electron problem. That means there's a lot of hard work. So another thing is that a different atom, you have different problems because this effective potential will be different for different atoms, right? Okay, so there is nothing like one size fits all. Every atom is a different quantum mechanical atom. You have to start from this very beginning. Even worse, even different atomic orbitals of one atom will be a different calculation, as we just look at solving 1s, solving 2s. In helium, there are different equations for you to loop. Okay, so quite involved things. It's not as simple as it looked at the outside. Okay, apparently it's very simple, but I hope that at least you appreciate the complexity of setting up this kind of theory. So at this point, I have left this effective potential as a function of the position of our single electron coordinate. But this is not a good thing to move on. Therefore, usually there's one more approximation to do. We want to approximate this effective potential due to Z-1 electron and the nucleus combined to be a central force. It only depends on the distance from the nucleus. This is called central field approximation. So there are two approximations actually involved here. Reducing it to single particle, that is independent particle approximation. Hartree, or another name called Hartree-Fock, they are behind the theory. Then after you have this single electron equations, it is our wishful thinking, at least we want to approximate this into that. Why? Because once we know this, we know the form of the solutions. Central force, single electron, we know the properties of the solutions. For example, we know that we can involve three quantum numbers, a principal, orbital angular momentum, Z component. And the theta phi part is this, must be. The energy depends on the first two quantum numbers, must be. Once we have central or spherically symmetrical potential. Okay, so with this nice feature in our toolbox, we will make this approximation. Then some of you, I think there was a question from a student about, are we making such an approximation, this and that, okay? Now, this box, well, optional, okay, is to summarize what are we making in terms of approximation. So for an atom, this is the formal Hamiltonian. All the kinetic energy, all the electrons seize the nucleus and pair by pair electron-electron repulsion. So this is the actual problem. Okay. So what we have done is the following. After we make all this discussion on the Z-1 electron and the nucleus, okay, producing an effective spherical potential. So let me introduce this potential here. All right. But I can play with the exact Hamiltonian. I add this term, I minus this term out. So I haven't done anything. So the second line, this line is still exact, the actual problem. But let's look at the remaining term. So I have this term, okay? I have the nucleus term, I have this term, I put it there. I add in a term, I subtract out a term, I add 0. So this is also the actual problem. What we are going to do is to focus on this problem, that is a single electron problem plus central force approximation. And then we ignore this part. This part has a name. It's called the residual electrostatic interaction. Whether this is a good one or a bad approximation remains to be seen. Look at the answer then, right? But at least in our mind, we hope this to be negligible. Therefore, we will not worry about this and we focus on the first term. So the first term is separable electron by electron, thereby we have single electron problems. So this is what we have done and we are going to do, okay? So let's look at this form roughly. What is this V effective as a function of distance from the nucleus? Okay, remind you, this effective include two things: attraction from the nucleus and repulsive term, on average repulsive term from the Z-1 electrons. Both are there. So now I would like to claim some electromagnetic theory result. So now if you have a charge, test charge, very far away from all the other charges, okay? So when you are here, you will see all the charges spherically distributed as if they are at the center. This is a result from electromagnetic theory, okay? So for this case number A, this test charge will feel such a force, okay? There is a second exercise that you did in E&M. If I have a spherical shell of charges and you are inside the shell, okay? At this position, the force in this bit will be canceled out by some force on the other side. Therefore, this charge, if you put a test charge at P, it feels no net force. Okay, so I'm just reminding you this two E&M results. So let's think about what is the functional form of this effective potential, roughly. This R is the position of the single electron state that we are focusing on. So it could be close to the nucleus, very far away from the nucleus, and everything in between, all right? So let's look at the two limits. When it is very far from the nucleus, all the Z-1 electron will be inside this position. Okay? Therefore, the net charge is seized. It's just 1, right? Because I have plus ZE, And then I have Z minus 1 electrons, so minus E. Okay, you sum it up, you only see plus E. Okay, that is the screening effect, you see, together. So when the position R is very far away, at that position, this effective potential is like seeing only one positive net charge of this form. However, when R is very close to the nucleus, because R is a continuous variable from 0, 0, 0 outward, right? So when it is close to the nucleus, all the Z minus 1 electrons are outside, like shells, okay? They will not have any electromagnetic force on the remaining single out electron. The electron will seize the whole nucleus. It will be much more attractive, okay? So all in all, you see these two limits. Very far away, it is like minus 1 over R. It is this dashed line here, extended from this thing, okay? So it goes like here, see my cross, the dashed line. Very close to the nucleus, it is an other behavior minus Z. This here goes like there, okay? But we actually don't know what's happening in between. That is the Hartree stuff, okay? Here we are trying to make quantitative argument. But if we know the two limit, we can just draw by hand in between. So we have some model like this. The effective charge is EZ effective as a function of position. So this is one possible model. But what I want to say is the following. If you understand the two limits, you realize it is not strictly Coulombic. Strictly Coulombic means it is always minus 1 over R, something up there is a constant. Now it's not a constant. Very far away is 1, close is Z, in between we don't know, all right? So it is not a constant, thereby it's not strictly Coulombic. It is good. It is not Coulombic, then we know from solving spherically symmetrical problems, the single electron state's energy should depend on two indices, N, L. What it means is that 2s energy will not be equal to 2p, and that is a fact for atoms. It is true, okay? So now we have a coherent story. The potential, even after we reduce it to single electron, it is not strictly Coulombic. Thereby, we expect for an atom, the 2s energy will be different from 2p. Which one is higher, lower? We will discuss it, but at least they are not the same. And then 3s, 3p, 3d, they will be different. Okay? It is reasonable because it's not strictly Coulombic. Okay? So now, let's take a break, and then we will discuss some hand-waving physics for atoms in general. All right?